In question 6, we're still going to use the idea of continuity and a sign chart to solve an inequality, but the only difference is we're going to have some more partition numbers on our sign chart. All the steps are the same as number 5. Again, I'll walk you through these steps. We're just going to have more partition numbers, and let's talk about why. So again, we're being asked to use a sign chart to solve an inequality. This inequality is already set to 0, so that part's nice. Remember how we talked about setting the inequality to 0 is going to help us think about positive values versus negative values, because if a function is continuous, the only way you can go from positive values to negative values is to pass through 0, to pass through that x-axis, unless there's a jump in the graph, right? That could happen at a hole. That could happen at a vertical asymptote. So that dynamic is going to come into play with a rational function, right? Because there could be holes, there could be vertical asymptotes. That could cause a jump in my graph, or all of a sudden, at one point, one side of the vertical asymptote I was down at negative outputs, and all of a sudden on the other side of the vertical asymptote I'm shooting up to positives. Or if there's a hole in the graph, I could be at a positive value, and then, then there's a hole and I jump down to a negative value. So those are just new partition numbers I have to consider. I didn't have to consider those in number 5 with a polynomial, because polynomials don't have holes and asymptotes and jumps and all of that, but rationals could. So let's find our partition numbers. Step 0 is already done, set equal to 0. Find the partition numbers. Okay, we're gonna have to think about 2 scenarios. So we're gonna start off just like normal. Where is the function output equal to 0? What inputs create an output of 0? And when I'm saying f of x, I mean this rational expression. That's my f of x. So just like with polynomials, I'm going to be concerned where does it hit the x-axis? Where is the output 0? That's one of the gateways, right? From going to positive outputs to negatives, crossing through that x-axis, the height of 0. But then I also have to consider holes and vertical asymptotes. So we have to know that happens, in this case, when your function, which is a rational expression, when the denominator is going to equal 0. Or if it simplifies and something divides out, there could be a hole. I'm already seeing that that's not the case, right? Because if I try to simplify this, the numerator is a difference of squares, so I can factor that difference of squares out. So I'll have an x minus 1 binomial in the numerator times an x plus 1 binomial in the numerator, but just an x minus 3 in the denominator, so it does not simplify. So there are no holes. I don't have to worry about that. But there are definitely values of x that would make this denominator equal 0, which would cause a vertical asymptote. So x minus 3 is going to be 0 if x is equal to a positive 3. So there would be a vertical asymptote at x equals positive 3. So that's going to become a partition number on our number line. And let's go back up here. Let's find where that function is actually going to equal to 0. So if I take my function, which is a rational expression, and I want to know where does that rational expression equal 0, the only way a fraction can equal 0, y'all, is if the numerator is equal to 0 and the denominator does not equal to 0. If you end up with a 0 in the numerator and a 0 in the denominator, remember that indeterminate form? That's when you had to see if it would simplify and something would divide out. We've already shown that that's not the case here. So we're just going to focus on finding values of x that would make the numerator equal 0 and making sure those values of x do not make the denominator equal 0. So let's go ahead and do that. If I set this numerator equal to 0, if I set x squared minus 1 equal to 0, I can factor it like I did down here, right? Like, so I've already factored that, and I could set the factors equal to 0 using my zero product principle. So I'll go ahead and do that real quick. X minus 1 is going to be 0 if x is equal to a 1. And x plus 1 is going to equal 0 if x is equal to a negative 1. Just to review some algebra real quick, I could also use the square root property. So I could isolate my square, my x squared, by adding 1 to both sides. And that would give me the equivalent equation x squared is equal to 1. And then I can take the square root of the left-hand side as long as I take the plus, positive, and negative square root of the right-hand side. So I'd end up getting x, the square root of x squared is x, is equal to plus or minus the square root of 1. Well, the square root of 1 is just 1, right? So x is equal to plus or minus 1. So either x is a positive 1 or x is a negative 1. I ended up with the same partition numbers using either method there. So I have 3 partition numbers to put on my sign chart. I have a partition number that created a vertical asymptote. So that'll go on my sign chart. And I have partition numbers that would make the function equal to 0. Okay, so let's start our sign chart. I draw a number line with 3 partition numbers. I have a partition number at -1. I have a partition number at 1 and at 3. The sign chart, the number line is indicating the inputs, the x values of those partition numbers. Above that, I'm going to describe what's happening to the outputs. So when x was a -1, that was the scenario where my output was going to be a 0. So I'm going to put a 0 up there. F of -1 created a 0. And the same thing happened at +1. When x was a +1, I had an output of 0. But when x was a 3, that was my vertical asymptote. That made my fraction undefined. So here I'm just going to write UND for undefined. If I put 3 into my function, I'm going to get something undefined. There's a vertical asymptote right there, right, at x equals 3. Okay, so now we're just going to do test points like we did in the previous problem. So I'm just going to throw those up real quick. Well, actually, let me calculate the first test point for y'all, just for clarity, and then I'll throw the others up. So when I say test points, remember you're looking at each segment of that sign chart, right? So I had 3 partition numbers. There's going to be 4 distinct segments. I have to test all 4 segments. So in this first segment, I chose an x value between -infinity and -1. So I just picked x equals -2, and I plugged that into the function, right? To this function up here that I'm comparing to 0. Okay, so when I plugged that in, I'm going to end up getting a 3 in the numerator and a -5 in the denominator. All I care about is the fact that that is a negative output. So I'm going to record that result by putting negative symbols above that segment of the sign chart. So any input, because this is a continuous function, that means for that entire interval from -infinity to -1, any input I pick in that interval is going to create a negative output until I hit -1, right? When I hit -1, my output is 0. So there's a potential for a sign change. I don't know if the sign's really going to change or not until I test a point in this next interval. So I need to test a point between -1 and +1. So 0 would be a really easy point to test. So let's go ahead and do that. Let's test x equals 0. I'm going to plug that into my function. That would give me 0 squared minus 1 over 0 minus 3. That's a -1 over -3. That's a positive 1/3. So now I have a positive output. So my output did change sign. That won't always happen. Don't assume your output's always going to change every interval. You could have 3 negative intervals in a row, 3 positive intervals in a row. It just so happened when I tested a point in the interval from -1 to 0, the output came out to be positive. So I'm describing that by putting plus signs above that segment in my sign chart. Okay, so now we'll just quickly pick some other test points. Let's pick, I don't know, x equals 2 as a test point, and then x equals 4. So I'm going to throw those into our function real quick. Okay, so when I tested x equals 2, I got a negative output. So I'm going to indicate that with the negative symbols in that region of the sign chart. And then when I tested x equals 4, I got a positive output. So I'll indicate that by putting plus signs above that region of the sign chart. Okay, so now I'm going to use this sign chart to solve the inequality. It happens to be the original inequality, right? So my inequality was already set to 0, so I didn't have to create an equivalent inequality. So we were wanting to know where that output where f of x is strictly greater than 0. It can't be equal to 0. Just strictly greater than 0. If you're greater than 0, you're positive. You're not equal to 0, you're not negative. If you're greater than 0, you're positive. So I'm going to come to my sign chart and find those positive regions. So positive region, I'm not going to include inputs that created negative outputs. I'm not going to include inputs that made the output 0. So I'm not including those. I'm not going to include inputs that made the output undefined. I'm only going to include the regions or those intervals that made positive outputs. So that is going to be x values from -1 to +1. And then I skip over and that I pick back up at 3 to infinity. Okay, so that is the solution to this inequality up here. When I go to solve this inequality, the solution is this set of numbers from any x value from -1 to +1 or 3 to infinity. If I pick any x value in either of those intervals and I plug them into this rational expression, the output I get is going to be greater than 0. So you can test yourself. I don't know. You can pick x equals 0. Plug that into that rational expression. When you do that, you're going to get 0 squared minus 1 over 0 minus 3. That's going to be a -1 over a -3. That's 1/3, and 1/3 is greater than 0. You could pick, I don't know, you could pick a whole bunch, right? There's an infinite number of solutions as long as the solution is in one of those intervals. Okay, I know these are tricky. I know they're tedious. I know there are a lot of steps. If you have questions, come see me in office hours or speak with one of our tutors, either an instructional associate or embedded tutor, or a tutor at the Learning Lab, or one of your classmates. Talk it out, y'all. Okay, good luck.